Deep beneath the ocean floor, ancient sediments hint that Earth's magnetic field sometimes changed far more slowly than expected. Deep beneath our feet, a restless ocean of molten metal helps keep Earth livable. The planet's magnetic field forms as liquid iron and nickel circulate through the outer core, generating electric currents that create a global magnetic shield. That shield is powerful, but it is not permanently locked in place. From time to time, Earth's magnetic north and south poles trade positions in events called geomagnetic reversals. The story of those flips is written into the planet itself. As sediments settle on the seafloor and rocks cool, tiny magnetic minerals can align with the field at that moment, preserving a snapshot that scientists can read millions of years later. These reversals are not quick switches. They typically unfold over several thousand years as the field weakens, becomes erratic, and the poles drift across the globe before stabilizing again with the opposite orientation. Over the last 170 million years, researchers have documented about 540 reversals, and many were thought to take roughly 10,000 years to complete. A new study led by a University of Utah geoscientist working with collaborators from France and Japan suggests that some reversals moved at a very different pace. The team identified examples from about 40 million years ago in which the transition stretched far longer, in some cases lasting more than 70,000 years. That extended timeline reshapes how scientists think about the magnetic field that surrounds Earth and helps block solar radiation and harmful particles from space. A prolonged weak phase could matter because the magnetic field acts like a planetary filter. When it falters, more charged particles can reach the upper atmosphere, potentially altering chemical reactions there and changing how energy moves through the climate system. Some effects could also reach the biosphere, especially for species that rely on magnetic cues. The amazing thing about the magnetic field is that it provides the safety net against radiation from outer space, and that radiation is observed and hypothesized to do all sorts of things. If you are getting more solar radiation coming into the planet, it'll change organisms' ability to navigate. It's basically saying we are exposing higher latitudes in particular, but also the entire planet to greater rates and greater durations of this cosmic radiation, and therefore it's logical to expect that there would be higher rates of genetic mutation. There could be atmospheric erosion. The results appear in Nature Communications, Earth and Environment. The lead author is Yuji Yamamoto of Japan's Kochi University. This finding unveiled an extraordinarily prolonged reversal process, challenging conventional understanding and leaving us genuinely astonished. Our paleomagnetists' job was to measure the direction and the intensity of the magnetization that's preserved in those cores. They don't know what triggers a reversal. Individual reversals don't last the same amount of time, so that creates this unique barcode. They can use the magnetic directions preserved in the sediments and correlate them to the geologic timescale. These sediments carry a reliable magnetic signal locked in by tiny crystals of magnetite produced by ancient microorganisms and from dust and erosion from the continents. Like a compass, the direction they point reveals Earth's polarity at the time the sediments were deposited. One 8-meter-thick layer took the scientists by surprise, appearing to record prolonged geomagnetic reversals in incredible detail. To achieve this resolution and to test if the strange magnetic behavior was due to changes in the magnetic field or the sediments. In subsequent analysis of these cores over several years, Lippert and his colleagues confirmed this was recording changes in the magnetic field and constructed high-precision timelines for two reversals, one lasting 18,000 years and another for 70,000 years. While the finding was a surprise, it may not have been unexpected according to the study. Computer models of Earth's geodynamo in the swirling outer core that generates the electrical currents supporting the magnetic field had indicated reversals durations vary, with many short ones but also occasional long drawn-out transitions, some lasting up to 130,000 years. In other words, Earth's geomagnetism may have always had this unpredictable streak, but scientists hadn't caught it in the rocks until now. Thank you for watching. If you've enjoyed our videos, subscribe to our channel for there's more to come.